Hello, I'll try to explain some things about quads and quadcopters. Okay, so the first thing we need to get clear is the actual orientations of the propellers and what they should do. So, if we watch here, we have 4 props, because it's a quad. Whoops. We got X mode. This here is a regular prop spinning counterclockwise, seen from above. This prop is also a regular prop spinning counterclockwise also. This is in order to get these two to thrust upwards. Okay. Then we need the pusher prop spinning clockwise, and the other pusher also spinning clockwise. Okay, clockwise, clockwise, counterclockwise, counterclockwise, pusher, pusher. This is the standard aeroquad setup that I'm using. Okay. We also need to make sure that these motors are actually spinning clockwise and counterclockwise. We can only adjust this by reconfiguring these 3 wires from the ESC to the motor. We need to experiment on that. Okay. So when these connectors are getting like spin the motor 50%, then the only thing telling which direction is these 3 wires. They need to be wired correctly. There's 50% chance that you get it right the first time, but you need to check it. Okay, now we'll check the data coming out of it in the configurator. This is the configurator 2.5 reversion, I think revision 471. No matter. We sensors are connected. They are sandwiched in between here. You can see this board is the nunchuck, and before that is the Motion Plus, and then in the middle we have this little magic black box, which we will evaluate and look at later. It's all set up on an M3 screw with a vibration damper and balsa board, and hot glued to the actual Arduino Mega. Also I've got rubber bands here to eliminate vibration induced by the contacts being loose, so that ain't supposed to be happening. Okay, so if I spin the quad clockwise, get it in my hand. If I spin it clockwise, the yaw gyro, rate gyro, will move to the right. It will move to the left if I spin counterclockwise. It's like looking at it this way from above, and then you're spinning it counterclockwise or clockwise. Counterclockwise will be counterclockwise on this one. It's velocity, so once the velocity is 0, it will become 0. Counterclockwise, stay 0. Okay. Axle C, not used in AKAQ code, but I use it for height regulation sometimes. If the quad's going down, it's going down. If the quad's going up, it's going up. Now, if I would actually lean it 90 degrees on the side, it will become 0. So that's because the gravity vector says so. Gravity affects C-axis 0 now. Now gravity affects C-axis negative, so the meter is negative, under 0, minus 105. If I flip it up right again, it will be 105. So there you have it. Actual pitch is actually the angle estimation made by the DCM algorithm. If I move it forward or pitch it forward, it will get below 0. Now it's saying minus 50 degrees. Now it's saying plus 50 degrees. Okay. If I move it roll it left, then axle roll will become negative. So I roll it right, counterclockwise, as seen from behind, then the meter will get positive in angles. Okay. Gyro roll, same thing, will go to the left if I move the quad to the left, but again, this is speed, velocity, angular velocity. Angular velocity is big, it goes much negative. Angular velocity is small, it goes not so big, negative number. But only for the time it moves. When it doesn't move, it should be 0. The same thing with gyro pitch. I pitch it forward fast, it goes down fast. And this is actually represented in the motor outputs, which we will use to evaluate. So I'll connect the sensor, the actual receiver now. There we go. Okay, now I've connected the receiver. I have armed it. I am in acrobatic mode. I put up the throttle to middle. I repeat, don't put on the motors now. No power to the ESCs, okay. What we will get is this. If the quad is level, the meters should be level, the motor bar plots. When I move it forward fast, then the front motors, front left and front right, front left and front right, those two should get more positive. Those should rise. I do that and they go up. Okay, up, up, up. If I move it to the left, back left and front left will go up. I move it to the left, they too go up. Okay, there. This is only temporary. This is only because of speed, angular speed. There, they go up. Other way, they go down. I'll try to match the heading here. Okay, they go down if I move it to the right, and then they counter the counter speed to break it down, to break the speed down when I try to stop it. Then we have the heading hold. Now if I this gets messy. If I would move this stick, yaw stick, to the right, now it has locked to this actual absolute heading. So you can see the number being -4 degrees or something. It's what it's locked to. So now it's locked. If I would turn it, then it would speed up back left and front right. The pusher, no, the regular propellers. Yes, here you see it. They speed up. This one and this one speed up, and that will cause the quad to yaw this direction to get to what angle I lock to. Okay. We'll also watch the artificial horizon here. It's when you're in acro mode, you don't really need to calibrate for 0 angle, but you need to do that now. So if I would have the quad placed like this, totally wrong, not aligned, but anyways, then the artificial horizon reads this. I do a calibration. I optimize the process a little to my new sensors, but it's the same there. And then you see the lights are flashing like this. Yeah, all around. That's a special code, but don't mind. The important thing is that the artificial horizon is level now. Okay, I move it forward, it goes down. Move it upward, it goes up. Left, it goes left. Right,